Okay, so we're going to learn some applications of the dot product. We're going to apply the dot product to find the angles in triangles in 3-space. We're going to apply the dot product to find vector and scalar projections, and we're going to apply the dot product to the physics application of work. So geometry is an application of the dot product. It can be used to find the measures of angles in a triangle and is useful to test whether a triangle contains a right angle. So here's our first question. A triangle has vertices at the point A, 3, 0, 2. Remember, this is a point, one capital letter, the point A, 3, 0, 2, B, 4, 3, 0, and C, 8, 1, negative 1. Determine the measure of each angle. So the first thing I'm going to do is draw a representative diagram. Obviously, I'm not going to draw one in 3-space. I'm just going to draw a representative diagram. And label my vertices A, B, and C. And we know that point A has the coordinates 3, 0, 2, and point B has the coordinates 4, 3, 0. Remember, this is just representative. And point C has the coordinates 8, 1, negative 1. And if I want to find angle A, so if this is a triangle in 3 dimensions, angle A is the angle between vector AB. So I'm going to draw in that vector. So the angle between vector AB and vector AC. So I want the angle between those vectors. I'll call it angle A, but it's the angle between vector AB and vector AC in 3-space. So right now we only have vertices, we don't have vectors. So to find vector AB, we know we can do that. So vector AB is B minus A. So vector AB is going to be 1, 4 minus 3, 3 minus 0, 0 minus 2, negative 2. And vector AC is going to be C minus A. So it's going to be 8 minus 3, 1 minus 0, and negative 1 minus 2. And then, according to the dot product, we can find this angle. We're going to call it angle A. So we can use the cosine of angle A is going to be vector AB dotted, the dot product of vector AB and vector AC, divided by the magnitude of each vector. So that's how we find the angle between two vectors, which is going to, in this case, be the angle at the vertice of this triangle in 3 dimensions. So now we can just carry this operation out. So vector AB is 1, 3, negative 2. And we're dotting that with vector AC, which is 5, 1, negative 3. The magnitude of vector AB is going to be the square root of 1 squared plus 3 squared plus 2 squared. So I'm going to do that kind of on my calculator here rather than writing it out as we get more used to these operations. So the magnitude of a vector, 1 squared plus 3 squared plus 2 squared is 14. So the magnitude of vector AB is the square root of 14. And the magnitude of vector AC is going to be 5 squared, which is 25, plus 1 squared, which is 1, plus negative 3 squared, which is 9. So 35. So I'm going to keep going here. So dot product is multiply and add, so it's going to be 5 plus 3 plus 6 over, and a property of radicals if you're multiplying them is that you can take the radical of the product, so square root of 14 times 35, which is 490. We're just making this really easy to evaluate with a calculator. So the cosine of angle A then is going to be 14, 5 plus 3 plus 6, over the square root of 490, which means angle A is going to be the cos inverse of that. Make sure you're in degrees on your calculator. So angle A is approximately, so the inverse cos of 14 divided by the square root of 490 gives me approximately 51 degrees. 50.768, but approximately 51 degrees. So now I have to use cosine law again to find one of the other angles, and then I can subtract from 180 to get the third angle. So it doesn't matter which one I find. I'm going to choose to find angle B next. So that would be the angle between vectors vector BA, and vector BC. So this angle in here, angle B, is the angle between vector BA. So vector BA I know is going to just be the same as vector AB with the opposite signs. So it's going to be -1, -3, +2. But vector BC, I would do C minus B. So vector BC is going to be 4, -2, 1 minus 3, -1 minus 0. So now we've got our two vectors we need again, so we can come up here and find the cosine of angle B, which is going to be BA dotted with BC divided by the magnitude of vector BA times the magnitude of vector BC. So the cosine of angle B is going to be vector BA, which is -1, -3, 2, dotted with vector BC, which is 4, 4, -2, -1, over their magnitudes multiplied together. So the magnitude of vector BA is the square root of 14, and the magnitude of vector BC is going to be 16 plus 4 is 20, the square root of 21. So the cosine of angle B is going to be, so dot product is multiply and add, -4 plus 6 minus 2 over the square root of 14 times 21, 294. So the cosine of angle B is going to be -4 plus 6 is +2 minus 2 is 0. Oh, and the cos inverse of 0 is 90 degrees. And see, we got the dot product to be 90 degrees, so angle B is 90 degrees exactly. So we have a right triangle actually. And then we can find angle C by doing 180 minus angle A minus angle B, which is going to be approximately 39 degrees. Okay, so there is an application of dot product to find angles in triangles and 3 space in this case. So here we have a 2-space question. Is there a right angle in the triangle with vertices P, Q, and R? So all we care about here is if there's a right angle. So we know that to have a right angle, the dot product has to be equal to 0. So I'm going to do a representative sketch again of a triangle. So my P is -3, -2. Q is -1, 4. And R is 5, 2. So say I want to check whether or not angle P is 90 degrees, because all I care about is if I have a right triangle or not. So I'm checking if angle P is 90 degrees. So all I really care about there is whether the dot product of PR and PQ is 0 or not. So I'm just kind of doing a test here. So I want to see what vector PR dotted with vector PQ actually equals. So vector PR is R minus P, so it's going to be 8, 4, dotted with vector PQ, which is Q minus P, so -1 minus -3 is 2, 4 minus -2 is 6. So dot product is multiply and add, 16 plus 24, which is 40, so there's no right angle at P, okay? So then I might want to check, is there a right angle at R? So then I would want to test whether RP dotted with RQ is 0 or not. So RP dotted with RQ, 0 or not 0. So RP is going to be -3 minus 5, so -8. -4, dotted with RQ, which is -6, 2. That's going to give me 48 minus 8, which is 40. And then I'm going to test angle Q. So I want to know QP dotted with QR. So QP is P minus Q, so -3 minus -1 is -2. -2 minus 4 is -6, dotted with QR, so 5 minus -1 is 6. 2 minus 4 is -2. So that's going to give me -12 plus 12, which equals 0, which means there's a 90-degree angle at angle Q. So therefore, there is a right angle in this triangle. So without having to go through and use the cos of an angle equals, if all they care about is if it's a right triangle or not, we can test whether or not the dot product of the two vectors at each angle when they're tail to tail is 0 or not. Okay, second application here. Projections are an important application of the dot product. Vectors are used in computer animation to determine the length of a shadow projected onto a flat surface. We use this idea to define the projection of a vector on a vector. So here's my picture. So here's a vector in 3 space being projected onto a 2-dimensional surface. So right here, this is the projection. Okay, and when we talk about the vector projection, we're talking about the magnitude and direction. And when they talk about the scalar projection, all we care about is the length of that shadow, I call it, the shadow of vector V on 2 space. So I'm going to derive formulas that we're going to be able to use. So we're looking at this diagram here. So we have a vector A that goes from point O, and we can say it's 0, 0, 0 to point A. And then we have another vector B, little b, that goes from O to point B, okay? And the angle between them when they're tail to tail is theta. And we can see that, so if this is my vector A, and pretend there's a light source coming from the top here. So this is all light shining down. So if we shine a light down, then the shadow of vector A onto this horizontal vector B is going to be this vector right here. So this vector in yellow highlighter is, you can think of it as the shadow of vector A on vector B, and that's our projection. So if we consider its magnitude and projection, it's the vector projection, and if all we care about is its length, it's called a scalar projection. So that vector from O to N is our projection of vector A onto vector B. So I'm starting off with this proposition here based on this diagram that the cos of the angle between them, so here's my angle, so this is my opposite because it's a right angle triangle. This is my hypotenuse, and this is my adjacent side. So I'm saying the cosine of this angle is the magnitude of vector O to N, which is the adjacent side, over the magnitude of vector O to A, which is our hypotenuse. So this is a true statement just based on SOHCAHTOA. Okay, so if we start off with that statement there, that we agree on that the cosine of that angle is the magnitude of vector ON over the magnitude of vector OA. And then we see that the magnitude of vector ON, so the magnitude of this vector, is the scalar projection. Okay, so the length of the projection of vector A on B. So if I want to get that by itself, I would just multiply both sides by the magnitude of vector OA, and I would get that the scalar projection is the magnitude of vector OA times the cosine of theta. So that's just multiplying both sides by the magnitude of vector OA and getting ON by itself. So another way to say, or the correct way to say the scalar projection here, or the length of this projection, is we say the magnitude of the projection of what? So of vector A. So projections written in normal size, we've got our magnitude bar. Vector A is written in normal size, but we're saying of vector A onto vector B is written as a subscript, so smaller, lower. So this is the magnitude of the projection of vector A onto vector B. Or we also can say the scalar projection. The magnitude of the projection, the size of the projection of vector A on B is equal to, so the magnitude of vector OA, I could also say the magnitude of vector A times the cosine of theta. And then to make a formula easy to use, often we pick things that we want to know or we have in the question. Multiplying by 1 is a good technique. And we can see that if we multiply by 1 by multiplying by the magnitude of vector B over itself, so really we're just multiplying by 1 in a strategic way, we can see that these three terms multiplied together constitute the definition of the magnitude of the dot product of vectors A and B. So the magnitude of A times the magnitude of vector B times the cos of the angle between them when they're tail to tail, we can write that, we can say that's the magnitude of vector A dotted with vector B, because that's its definition. Okay? So that takes care of the numerator, and then over the denominator, which is the magnitude of vector B again. And there's our formula for the scalar projection, or the length of the magnitude of this vector here, vector ON. So the length of this vector can be found by doing the magnitude of vector A dot B over the magnitude of B. Now what if we also want a direction? So we want so this is the scalar projection here, or the magnitude of the projection, length of magnitude of projection. But now we want the vector projection. We want it as a vector starting at 0, 0, 0 and ending somewhere. We want the vector projection. Okay? So the vector projection won't have the magnitude bars around it, but we still use the same type of notation here, the projection of vector A onto vector B. So it's going to have the same length here. It's going to have the same length. But these magnitude bars here mean that if I take the absolute value of a number, because the dot product is going to give me a number, I could get dot two vectors together and get a negative. And this absolute value bar, because this is a length, prevents me from using that negative as a directional association. Okay, so we want to remove those absolute value bars. So we want to say that the vector projection, we could get a negative dot product and that have meaning as far as direction goes over the magnitude of vector B. So right now we've got the same length. Okay, so this vector is going to have this length right here. This vector here has that length, but it's in the direction of vector B. So we could multiply it by B hat. So here's the magnitude, here's the direction, because B hat is a unit vector in the same direction as vector B. So I'm taking the length of it and multiplying it by a vector in the direction of vector B. But we know that according to the formula for finding a unit vector, we know that the definition of a unit vector, in our case B hat we want to talk about, is vector B over the magnitude of vector B. So I can change B hat to vector B over the magnitude of vector B. So that the vector projection of A on B is, so if I look at what are the numeric parts, so I've got A dot B is a number. If I multiply the denominators together, I get the magnitude of vector B squared, which is also a number, and I'm multiplying that by vector B, which is a vector. So I've got this number, the scalar, multiplying by a vector, which I can do. I can figure out what this scalar, this number is, and then multiply it by each component of my vector, and I'll have the vector projection of A on B. So that's our formula. And to remember these formulas, you'll have them in front of you when you're doing the work, but if you had to memorize them for a test, I always say the little one does all the work. So if you look at this, projection of A on B, we only see A once in the formula. A dot B over the magnitude of B squared times a vector B. And same thing with the scalar projection, the little guy does all the work. A is there once, magnitude of A dot B over the magnitude of B. So that's my development. Here I just have them for you again, okay? Vector projection and scalar projection, same kind of diagram setup, but without the proof, but then just your formulas there. So again, this is what we're looking at here. This is in yellow. This yellow vector here is the projection of A on B, the vector projection. And then if I just want to know its length, that's the scalar projection. Okay? All right, so if vector u is -1, 4 and vector v is 4, 3, determine the projection of vector u on v, illustrate the result on a diagram. So first let's use the formula and then we'll show how the diagram enhances our understanding of what the formula tells us. So the projection, the vector projection of u on v is u dot v over the magnitude of v squared times vector v. So u dot v over the magnitude of v squared. So that's going to be 16 and 9 is 25 squared times vector v, which is 4, 3. So our dot product is going to be -4 plus 12 over, so the square root of 25 squared is just 25, okay, because squared undoes square root, times 4, 3. So -4 plus 12 is 8 25ths times vector 4, 3. And then I would see, can I reduce 8 25ths? No. So then I would just multiply, so I get 32 25ths, 24 25ths. So that means the projection, the vector projection of u on v should be a vector that starts at 0, 0 and ends at 32 25ths, 24 25ths. So let's draw a picture here and see if that jives with what we got. So vector u we can draw. We know it's a vector that starts as 0, 0 and ends at -1, 4. So here's vector u. And vector v starts at 0, 0 and ends at 4, 3. So here's vector v. And we want the projection of vector u, the orange one, on to v, and we always assume that the light source is always coming perpendicular to the vector that we're projecting onto. So in this case, we're projecting onto v, so our light's coming perpendicular to vector v. And you can see that here's our light shining on, perpendicular to vector v. It looks like, so I like to try to make it look like a 90-degree angle here. Protractor's good, but should look like the shadow of the tip of vector u on vector v looks like meets at 90 degrees. And then this vector here that I'll show in red, starting at 0, 0 and ending there, would be the projection of vector u on vector v. So this vector here is the projection of vector u on vector v. And it should look like it's 32 over 25. So from 0, 0 to 32 over 25. So in the x direction, about 1.28, which looks good. And then 24 over 25 is just under 1, which looks good as well. So our diagram makes sense with our calculation. So if vector A is the vector 2, 4, 1, so now we're in 3 space, and vector B is the vector 3, 3, 4, then find the vector projection of vector A on B. So again, just writing the formula out helps me. So I know that the vector projection of A on B is going to be, the little one does all the work, A dot B over the magnitude of B squared times vector B. So A is 2, 4, 1. Dotted with B, which is 3, 3, 4, over the magnitude of vector B squared. So I'm going to get my calculator to do this magnitude calculation. So it's going to be 9 plus 9 plus 16, square root of 34, but we're squaring that. That's what often gets forgotten. And then we're multiplying that, whatever this number turns out to be, by vector B, because we want the vector projection. So then we'll do our dot product here. So that's going to be 6 plus 12 plus 4 over 34 times 3, 3, 4. So 18 to 22 over 34 times 3, 3, 4. Reduce 22 over 34 so we can divide top and bottom by 2. And that's going to give me 11 over 17 times 3, 3, 4. And then just multiply, so 33 seventeenths, 33 seventeenths, 44 seventeenths. So that is our vector projection of vector A on B. It would start at 0, 0, 0 and end at that point, or as a vector, it's an ordered triple. Now we want the magnitude of the projection of vector B on A. So the little one does all the work, so that's going to be according to our scalar projection formula. Remember, it's different from the vector projection formula. But this time it's B on A. So it's going to be B dot A, the magnitude of, over the magnitude of A. So the magnitude of B, which is 3, 3, 4, dotted with A, over the magnitude of vector A, which is the square root of, so that's 1621. So the magnitude of this dot product here is going to be the magnitude of 6 plus 12 plus 4 over the square root of 21. So the magnitude of 22 over the square root of 21. So what does the magnitude of 22 mean, or the absolute value of 22? It just means it's a distance from 0. It's always positive. So in this case, it's just 22 over the root of 21. So that's our exact projection of vector B on A. It's a number, again, scalar projection, how long it is. Or you could find out what it is approximately if you need to. 22 divided by the square root of 21. Oops. 22 divided by the square root of 21. It's approximately 4.8. Okay, if U equals, vector U is vector 5, 6, negative 3, and vector V is vector 1, 4, 5, then find the projection of U on B. So the projection of vector U on vector V is going to be U dot V over the magnitude of vector V squared times vector V. So 5, 6, negative 3, dotted with 1, 4, 5, over the square root of, so the magnitude of vector V squared, so it's going to be 25 plus 16 plus 1, squared, times vector V, which is 1, 4, 5. So doing the dot product is multiply and add. So 5 plus 24 minus 15 over 42 times 1, 4, 5. So that's going to be 14 over 42 times 1, 4, 5. I think 14 goes into 42. So you can divide top and bottom by 14, yep, and you get 1/3. That's nice. So that means the projection, the vector projection of u on v is 1/3, 4/3, 5/3 as an ordered triple. If A and B are two non-zero vectors and the projection of A on B is the zero vector, what conclusion can be drawn? So if we look at the formula, projection of A on B, we know, and it's vector projection, we know that it's going to be A dot B over the magnitude of B squared times vector B. So if we look at this, it's two non-zero vectors, so we know that the magnitude of B squared is not 0. And we know that this is not the zero vector. So the only thing that can be 0 here, so that our dot product gives us 0 times a vector, which gives us a 0 vector, is if the dot product were equal to 0. So what do we know about two vectors if their dot product must equal 0? It's that the two vectors are perpendicular to each other. So A must be perpendicular to vector B is the conclusion that you can draw. The two vectors must be perpendicular. And that makes sense here. If I go back to this diagram for a minute, if u and v were already 90 degrees to each other, then the shadow of the tip of vector u on vector v would just end up at 0, 0 again, and you would have the 0 vector starting at 0, 0 and ending at 0, 0. So it makes geometric sense as well. It's algebraic sense. All right, our last application of the dot product is work. Work is done, this is physics, from a physics standpoint, okay? Work is done when a force causes an object to undergo a displacement. The work done is the dot product of the force vector and the displacement vector. Work is a scalar though, okay? So work is F dot D. We know that a dot product gives us a number or a scalar, okay? And we also know, so this is dot product here, and then we know that the magnitude of the dot product is the magnitude of one vector times the magnitude of the other times the cos of the angle between them when they're tail to tail as shown in this diagram. Okay? So when a force causes an object to move, the work done is the dot product of the force and the direction. Displacement vector. So work is measured in units called joules. So if you're not a physics person, joules is the unit work is measured in. It's also in Newton times a meter. So an object is dragged 5 meters horizontally under a constant force of 30 newtons applied horizontally. Find the work done. So I would start off with my formula, work equals F dot D, and then even the magnitude of the force times the magnitude of the displacement times the cos of the angle between them when they're tail to tail. So the magnitude of the force is 30 newtons. The magnitude of the displacement is 5 meters. Now the angle, the object is dragged horizontally and the force is applied horizontally. So both forces are in the exact same direction. So that means the angle between those vectors when they're tail to tail is 0, sorry, not theta, it's 0 degrees. And the cos of 0 degrees is 1. So the work in this case just ends up being 150 joules. A child pulls a toboggan 100 meters at a constant force of 200 newtons applied at an angle of 40 degrees to the horizontal. Calculate the work done. So if you were making a little diagram here, so here's our toboggan, and its displacement vector is going horizontally, and its force vector is applied at 40 degrees to the horizontal. So here's my force vector, and I know this angle's 40 degrees. So the work done is going to be F dot T, or the magnitude of the force times the magnitude of the displacement times the cos of, it's going to be 40 degrees. I'll write theta for now, and then I'll fill them in. So the magnitude of the force is 200 newtons. The magnitude of the displacement is 100 meters. And the angle between them when they're tail to tail is 40 degrees. And then I can do that calculation in my calculator. So 200 times 100 times the cos of 40 is approximately 15,320.9 joules. An object is dragged 5 meters on level ground by a 20 Newton force which is applied at an angle of 50 degrees to the ground. It's then dragged 10 meters up a ramp by the same force. If the ramp is inclined at a 30-degree angle, find the total work done. So we're going to draw a diagram. I think that will help us with this. So we've got like our level ground. And then at some point we have a ramp that's inclined at 30 degrees. I'm not going to use a protractor. I'm just going to say that this is 30 degrees here. And there's our ramp. So I'm going to divide it into two different works. So our total work is going to be like work 1 plus work 2. So the first part, we're dragging our object 5 meters. So here's our, we're going along horizontal ground. So here's our displacement vector 1. And we're doing it at an angle of 50 degrees with the ground. So this angle in here is 50 degrees. And this is our force 1, call it, okay? And then we also, once we get up onto the ramp, we're moving this way, right up the ramp. So this is our displacement vector 2 is in that direction, but it says our force is the same. So if our force is at 50 degrees to the ground, but this 30 degrees of our ramp is making up 30 of the 50 degrees, that means if I use the exact same force, so I bring this force over here, so it's parallel to force 1, but 30 degrees is being made up by the ramp, there's only 20 degrees this time between the force and displacement. So that's my thinking there. So my total work is going to be work 1, which is the magnitude of F1 times the magnitude of D1 times the cos of theta 1, plus work 2, which is going to be the magnitude of F2 times the magnitude of displacement 2 times the cos of theta 2. Then we can substitute in our numbers. So the forces, the magnitude of the force is 20 newtons. On level ground, its first displacement is 5 meters. And the angle between them when they're tail to tail is 50 degrees. Now when I'm on the ramp, the force is still, the magnitude of the force is still 20 newtons. It's dragged 10 meters up the ramp, but the angle between the force and displacement now is only 20 degrees. And then I should be able to enter that into my calculator all at one time. So I've got 20 times 5 times the cosine of 50 degrees. And then make sure you're in degrees. And I'm adding on, in brackets, 20 times 10 times the cosine of 20 degrees, which ends up giving me approximately 252.2 joules. So that would be my total work done. It's kind of a word problem, so you could say therefore total work done is 252.2 joules. Question 4. Calculate the work done on an object if the force in newtons can be described by the vector F equals 548 and it's being moved from position A at -710 to position B at 58, -6, where displacement is measured in meters. That's important because the definition of work requires that force be measured in newtons and displacement be measured in meters. And we know our force is in newtons and can be represented by that vector. And we know our displacement is in meters and can be represented by a vector as well. The vector from, so our displacement vector is the vector from point A to point B, which we know is B minus A. So 5 minus -7 is 12. 8 minus 1 is 7. -6 minus 0 is -6. So now we've got a displacement vector and we've got a force vector. So this makes it really easy to do our dot product work equals F dot D, we can just do our dot product of vector 5, 4, 8 dotted with vector 12, 7, negative 6. And that's going to give me 60 plus 28 minus 48, which is going to give me 40 joules. So when our force and displacement are given to us as vectors, it's really easy to do the dot product. And that is the lesson. So the 3 applications of the dot product we looked at, we're finding it at angles and triangles in 2 space and 3 space. Vector and scalar projections of a vector on a vector, and finding work.